All right, we're going to take a look at classifying chemical reactions 4.2. And I believe this is going to be the end. We're going to break the test into two parts or something like that, because this, along with the chapter 3 in this, is a pretty long topic. So I kind of want to break it up so it's not too much to study. Anyway, classifying chemical reactions. Before we start talking about chemical reactions, let's talk about the idea of soluble versus insoluble and electrolytes. And we're going to approach this again. Something that is soluble is simply something that it dissolves in water. And we're going to talk about exactly why and how something dissolves a little bit later when we start talking about energetics and interactions and entropy and enthalpy and all that. But right now, if something is soluble, it dissolves in water. Strong electrolytes are ionic compounds that completely dissociate in water. So when I say they dissociate, so first of all, completely dissociate is what makes them soluble. So I'll go down here to A, example 4.3a. Sodium chloride is going to completely dissociate into Na plus aqueous and Cl minus aqueous ion. So whenever I drop any sodium chloride into solution, it turns into sodium plus and chloride negative Cl minus ions, and completely there's 0% of the sodium chloride remaining. It's all in this aqueous form. So strong electrolytes completely dissociate into their ions. There is none of that left when we get down to it. So in terms of what classifies as a strong electrolyte, there are three things that classify as strong electrolytes. Any soluble ionic compounds, and I'm going to give you a list, strong acids, and strong bases. So first of all, the soluble ionic compounds and the strong bases, they're all going to be on a list, so we don't have to worry about differentiating those. Basically, there's a handful of them that we have to worry about. The strong acids are the only new addition to this that we have to memorize. So soluble ionic compounds, strong bases are all on the same list. And then strong acids, that's something we just have to know from experience. So for example, 4.3 showed the dissociation of these things, and we should have done it on the previous a little bit. So when I was breaking apart ions on the previous one. So what do these dissociate into? So again, we've already done this a couple of times, but it's always good practice. How do I know that these things are ionic? They have a metal present or a polyatomic present, and that's immediately how you know that they're going to be electrolytes. And then we have insoluble. So first of all, insoluble does not mean that it is completely does not dissociate in water. What this means is it partially dissociates. Actually, sorry, I should say the term a weak electrolyte means that it partially dissociates. Insoluble basically means that it does not. And it seems like if you drop something into solution and it doesn't dissolve, it does not, I want to say completely dissolve in water. Partially dissociates in water. So when I say it partially dissociates, and we're going to get to this later, so right now we can just assume that it does not dissociate at all. But if I look at my first example of silver chloride here, silver chloride is a solid and it only partially dissociates. So it turns into Ag plus, aqueous, and Cl minus aqueous. But it also kind of stays, there's a double-sided arrow here. So the silver chloride turns into silver and chloride, but the silver and chloride also come back together to form the solid. Ultimately, what this means is you pretty much do not have, I would say that you have about 0.01% of it is in that form, and the rest, 99.99%, is in that form. So when we're looking at something that is insoluble the majority of it, in fact, almost all of it, is completely non-dissociated. So this almost does not happen. It does happen, but at a very, very small rate. Okay, so we use double arrows. So for every single one of these, I want you to use a double arrow, and you may see them both ways. But tell me what these should dissociate into. Although, again, we're not really going to worry about them actually dissociating. So they just partially dissociate. You might get a couple of ions in solution, but not a complete dissociation like you do. So up here, on the other hand, I have like 100% sodium chloride, and I absolutely have none of the sodium chloride left. So it all turns into product. And that's why the double arrow exists. If it's all product, we don't have to ever, we never go back, right? But for silver chloride, we absolutely do. So soluble and insoluble compounds, insoluble ionic compounds, basically it's not soluble, it's going to be insoluble, and then weak acids and weak bases, and we're going to get used to those as well. Weak bases are simply non-soluble hydroxides. And again, we're going to take a look at what all of this means. All right, here we go. So precipitation reaction. So this is the first one where we run into insoluble compounds. And actually I will do this demonstration, assuming I have a place to dispose of the lead. So I have a solution of potassium and iodine, so Ki, aqueous, but I know Ki is soluble. So what I really have is I have K+ ions and I- ions in solution. So those are going to be combined together with lead nitrate. But what I know I really have are lead ions and nitrate ions. So that's really what is in solution. Okay, so I'm combining these two things together. And what is the result of that? Well, once I mix them together, we find out that what we find out is that here are my nitrates. Here are my, what are the sodiums? Just want to make sure, potassiums, yeah. And this right here are my lead iodide molecules. So they have found each other and they've started to come together and form a solid, because we know that that is a solid. And that's what you're seeing, this yellow here is the lead iodide. And it's going to be here on the bottom. So overall, what ends up happening is lead iodide forms a solid, leaving behind the solution. So we have lead iodide solid. And I have potassium and nitrate ions. Okay, we'll get into what we call these. So in this reaction, we noticed that lead nitrate was aqueous and potassium iodide was aqueous. We produced lead iodide, which turned out to be a solid, and I had potassium and nitrate. So we're going to combine those together and just say aqueous. It's just a shorthand for those are aqueous. So the end result is I have created, the only thing that I really care about is the fact that I created that solid. Okay, so again, lead ions combined together, they find the iodine ions in solution, and they create this lead iodide solution. Okay, there we go. Create this lead iodide, which starts to form this solid. Okay, so that's a precipitation reaction. We mix two things together and we create a precipitate. An insoluble solid forms because we have combined things together that form an insoluble ion. So this is the solubility table. Okay, so I'm going to hand one of these out, or at least I will have. You'll have access to this. You won't have access to this on an exam, so you'll have to know some of these. But let's take a look at what we've got. So first of all, we have soluble ionic compounds. So this means that anything that contains, and we're usually looking at the anion here, anything that contains these anions is going to be aqueous. Okay, so everything here is soluble. So anything containing nitrate, chloride, bromide, iodide, those are the halogens, sulfate, and acetate are going to be aqueous. Except there are a handful of exceptions. So there are no exceptions for nitrates and acetates, meaning if you have acetate or nitrate, they are always going to be soluble. Doesn't matter what they're with. If it's an acetate or a nitrate, always soluble. But there are a couple of examples where you do in fact have some type of exceptions. So any chloride, bromide, or iodide with silver is going to be considered a soluble. So this actually, these are all going to be insoluble. So they're going to form solids. So these are all insoluble. These are all soluble. Okay, so AgCl is going to be insoluble. Hg2Cl2 is going to be insoluble. Now I'm getting it from just here. Ag plus bromide, so AgBr is insoluble. Strontium plus sulfate, SrSO4 is going to be insoluble. Barium sulfate, mercury sulfate, lead sulfate, all of those things are going to be considered insoluble. Okay, so again, insoluble compounds will form solids when they find each other in solution. Now we have insoluble ionic compounds. So again, we're looking at the anions, and basically everything here is going to form a solid, except with these exceptions over here, these are all going to be aqueous. So we're going to look at the ions. If we recognize that they're soluble, then we check the chart and notice it's kind of limited. So the exceptions are compounds of NH4 and the alkali metal cations. So you'll notice that all of those have those. So these compounds of, so anything that has NH4 plus or group 1 are going to be soluble. So if you see group 1, immediately say, oh, that's soluble. If you see NH4, immediately that's soluble. And then the rest of it is calcium, strontium, barium for sulfide, calcium, strontium, or barium for hydroxide. And we're going to talk about those just a little bit more. But again, group 1 and ammonium ion, those are all soluble always, no matter what. And then anything with any sulfide or hydroxide with calcium, strontium, or barium. And what you're going to notice is calcium, strontium, and barium are the heavier parts of group 2. Everything else is considered soluble. Okay, so or considered insoluble, I should say. Okay, so we'll get to use this a bunch more, and we're going to see how it all kind of comes together. But you're going to need to see that. Why do we need to know that? Well, we have this metathesis reaction. So cations and anions are going to exchange partners. So if we have a metathesis reaction, and the classic, and I don't think I have it here perfect, I don't. So if I have something like sodium chloride plus silver nitrate, this is the one that we're going to probably do a bunch of. What does that actually look like? So let's take a look at what we know about these things. So silver chloride. So first of all, we have to decide the phases of these individual things. Actually, before we even do that, let me take a look at these. So say sodium chloride, and so here's my sodium. I'm going to use different colors for this to make it more evident. Here's my chloride. Here's my silver. And here is my nitrate. Okay. So what we're going to do is we're going to have the cations. We're going to have them switch partner with the anions. So the silver and the chloride came together, but on the other side, we're just going to have them switch partners. And the way I like to look at this is, let's see what we actually have here. So I have Na plus, Cl minus, I have Ag plus, and NO3 minus. On the other side of the coin, what I'm going to do is I'm simply going to say, all right, well, sodium could combine with chloride, which it already has, or it could combine with nitrate. So on the other side, we've already have that one. So we're going to have the other option on this side, and I'll use blue. So we have NaNO3 on the other side. And then the silver was with nitrate, but it could also be with chloride. So we're going to switch partners and have AgCl on the other side. Okay, and so that's essentially what's going to happen. So if we look at this thing using what I have here, the silver and the oops. So the nitrate was with the silver, and now it's going to combine together with the sodium. The chloride was with the sodium, now it's going to combine together with the chloride. So this is a metathesis or an exchange reaction. They're essentially just exchanging partners. Okay. And in fact, maybe I could just erase the colors from. So sodium and silver switch partners, or the cation switch, anion switch partners, however you want to think about it. That's how it looks. So now we're going to go back to the solubility table. So sodium chloride and ACl. We already know this answer because it's got group 1. So we don't even need to check our solubility table because sodium is group 1. Sodium is group 1 means this is aqueous. Anything ammonium ion, group 1 is going to be soluble. That means the same thing for sodium on the other side. Both of those are aqueous. Okay. Next up, let's take a look at silver nitrate. Well, again, we don't have group 1, but we do have nitrate. So let's take a look. What do we know about nitrates? Nitrates are soluble and there are no exceptions. That means that my silver nitrate is in fact aqueous. And now finally, silver chloride. Silver chloride, what do I know about chlorides? Chlorides are soluble except for silver, mercury, and lead. So there it is. I do have silver chloride as the exception. So this is going to form a solid. Okay, so these are metathesis reactions, and we're going to worry about balancing them. In fact, we're going to balance them in class, or we will balance. Well, let's actually do this one. So do example A, and then we'll work through it together. Okay, so pause me and try example A here. All right, so here we go. K plus SO4 2 minus, and I have Ba 2 plus and Cl minus. So remember, before these two and these two are together, but when we combine them in the same solution, now they can seek other partners. So the barium and the sulfate are going to combine together to give me a new compound. Potassium and the chloride are going to combine together to give me a new compound. So barium sulfate becomes barium sulfate, and potassium chloride becomes potassium chloride. So now I have barium sulfate and potassium chloride, and anything with group 1 we know is going to be aqueous. We always need to add phase tags to these things. Barium chloride. So let's take a look at barium chloride according to my list. So barium, so there are chlorides, lead, mercury, and silver. Barium chloride is not on that list. So if it is not in the exception, it means it's over here. Okay, so it is not soluble, it isn't, or it is not insoluble, it is in fact soluble. So that means that we are going to say that this is aqueous. How about barium sulfate? So what do we know about sulfates? Let's check. Here are my sulfates: strontium, barium, mercury, and lead. There's barium, meaning it is not a regular sulfate, it is an exception, therefore it is insoluble. It's going to get a solid phase tag. Great. So now it's just a matter of balancing. And before, on the previous chapter, we talked about balancing these things, but we can actually go a lot quicker instead of going through and putting the list underneath, although we did that, and that's great. You know how to do it that way. I find it's much easier to just go back and forth. So here we go. This is how I would do it. Let's start with potassium, because that's our first ion. 2 potassiums here, 1 potassium here. So I'm going to toss a 2 in front to create 2 potassiums. 2 potassiums, 2 potassiums. 1 sulfate, 1 sulfate. 1 barium, 1 barium. 2 chlorides, 2 chlorides. Okay, so you can just kind of go back and forth, bounce back and forth, and balance them that way. But there you go. Barium sulfate is a solid. Potassium chloride is an aqueous solution, but we have two of them just to balance the equation. All right, so do the rest of those and let's keep going. So the molecular equation, we just created the molecular equation by switching ions. So in this case, lead and potassium are going to switch partners and give me potassium nitrate and lead iodide. And we've already done the solubilities for these. So all nitrates I know are aqueous. Potassium iodine has got group 1, so I know that's aqueous. Lead iodide we found out was solid, and potassium nitrate is aqueous. Again, I know those phase tags because I looked at the solubility table. So this is called the molecular equation. Let's balance this out. Again, I've got one lead, got two nitrates, I have one nitrate. So let's toss a 2 in front and let's start again. One lead, two nitrates, one potassium, two potassium. So let's throw a 2 in front. And one more time we check. One lead, two nitrates, two potassiums, two iodides, Good, we're balanced. So just kind of go back and forth until you get it. So here we have the balanced chemical equation. So in order to write the complete ionic equation, we are going to write an equation with all soluble strong electrolytes written as ions. So anything that is aqueous is going to turn into its ion. So we have 2+ aqueous and nitrate aqueous. I don't really care. I know there's 2 of those nitrates, but I don't really care that it's balanced, and we'll see why in a bit, because I only care about the initial molecular and the net ionic. So let's not worry about adding 2 in front of that nitrate. Potassium iodide is also aqueous, so K+, I-. My arrow. Lead iodide is a solid, so I'm just going to rewrite it. And then potassium and nitrate, because they're both aqueous as well. So let me rewrite this whole thing. Lead, aqueous. In fact, I'm just going to not write the phase tags. I will in the beginning and the end, but if it does not have a phase tag, it is going to be aqueous, just for brevity. We will add the solid phase tag because it is in fact solid, not aqueous. K+ and NO3-. We can balance it if we want to, but ultimately I don't really care. That is a complete ionic. Now I'm feeling like I need to actually balance it, so let's do it. There were 2 nitrates. There were 2 of each of these, and it just kind of gets in the way, and you'll see why in a second. 2 of those, 2 of those. So there you go. There's the balanced one, but you don't need it because this last part is kind of where we are. So the net ionic is an equation that includes only the ions and molecules directly involved in the reaction. Essentially, it's the only ones that become the solid or that do change. So let's take a look. So I have, and you could do it with this whole thing, but I'm going to do it up here. So I have lead is aqueous here. Lead on the other side is solid. So I'm going to leave lead alone. Lead is part of the reaction because it changes. It's interesting. Lead is interesting because it goes from aqueous to solid. So we're going to ignore it. Nitrate is aqueous on this side and it's aqueous on that side. So it is not interesting. I'm going to cross it out and I'm going to add it to the list of spectator ions. Nitrate basically is not doing anything other than charge balancing. It's there to bring lead to the table. Okay. Potassium is aqueous here. Potassium is aqueous over here. So we could eliminate potassium as well. And I'm also going to add that to the list of spectator ions. Again, no direct role in the reaction. It's aqueous on the left, aqueous on the right. It doesn't do anything other than bring the other ion to the party. And then finally, iodine goes from aqueous to solid. So that one is important. We are not going to erase it or write it. So let's rewrite everything that remains. I had lead ions, and this time I will include phase tags, aqueous, plus iodine, which is aqueous. And that yields the lead iodide, which is solid. Boom, there we go. We have everything. The only thing we have to do is make sure that we balance it. this and the molecular are the most important equations to be able to write. So the net ionic equation includes only the things that change, okay? We have spectators. These spectator ions, again, are just there to bring charge compensation or to bring the other one to the party. And that's pretty much it. So these are precipitation reactions because you always end up with a precipitate at the end. You always end up with a product that is a solid, okay? Good. So do these examples. I want the complete ionic, and most importantly, I want the net ionic and the molecular. So give me the molecular, the complete, and the net ionic for these. Okay, same here, same here, same here. These are important to practice, so we practice a bunch of them. Okay, so that's precipitation reactions, and now let's take a look at acid, base, and neutralization reactions. So it's pretty much the same thing in terms of a metathesis reaction, but we have to kind of talk about what acids and bases are. So acids are a compound. There's a bunch of different definitions, and we're going to get into this a little bit more. Compound that adds H plus to solution is the good as a decent definition. This is the Bronsted-Lowry definition, but adds H plus. So anything that has H out front is going to be an acid. Okay, there are two different types of acid. A mineral acid is basically an acid without carbon. So we're looking at the H plus combined with a polyatomic, So as an example, or binary acids, binary. So something like HCl, HBr, HI, all of those are going to be considered mineral acids, as well as something like H2SO4, HNO3. Again, no carbon involved. Organic acids are basically H plus in the form of COOH, which is the organic functional group, and it kind of looks like this: carbon with one oxygen and then this other OH there. And we're going to talk more and more about functional groups, and I'll put an R here. That's just other organic stuff, a bunch of carbon and other stuff. So this is the acid that is acidic. That's the one that produces H plus in water. Okay, so anytime you see COOH or CO2H, you see that less, but you will see that, or H out front, HCOOH. In fact, that one is actually the acidic one, but that's formic acid. You're going to see a bunch of these. Anytime you see COOH, it's an organic acid. Monoprotic, diprotic, polyprotic. It will produce, monoprotic produces one H plus in solution. Basically H with anything else. Anytime you have just one hydrogen with an anion. Diprotic produces two H plus in solution. So H2 and some other stuff. A polyprotic produces 3 plus in solution. So, and I guess I should also do the organic version, HCOOH. That would be one proton there. Polyprotic is something like H3PO4 is the best example we would have. Again, 3 acids. By the way, citric acid produces 3. It's like H3 and then a bunch of other organic stuff. So H3X. Okay. Good. So that's it. It's going to produce H plus in water. We recognize acids because of the COOH, but more importantly, because the H is out front. Bases. Bases produce OH minus in solution. That's the Arrhenius definition. We're going to talk about different definitions, but produce OH minus in solution. So something like NaOH breaks into Na plus OH minus. So the fact that it produces the OH minus, that's going to make it a base. So strong acids and bases, just like a strong electrolyte, because they are strong electrolytes, they completely dissociate in water. So completely dissociate. There are 2 lists here. So the acid list is the one that you're going to have to know. the strong bases. So here are the strong bases. What you notice is instead of looking at this list as your strong bases, just recognize that as the soluble hydroxide equal strong bases. It is, the strong bases are simply group 1 and heavy, there we go, group 2 hydroxides. So calcium, strontium, and barium, if you look at periodic table, you're going to notice that they're the heavy ones. Okay, so group 1, if you have group 1 hydroxides, and the heavy group 2s are the strong bases, everything else, and they're essentially the soluble hydroxides. Yeah, so that's how you recognize those. Group 1 and heavy group 2 are the strong ones. In terms of strong acids, so take a look at a periodic table. What you notice that there's a little division here. HBr, HCl, and HI. Those are all strong acids. What you notice is not on, those are all halogens, but what you notice is not on the list is HF. It's a good example of a weak acid. HF is a weak acid. And ask me during class about HF because it's kind of scary and crazy. So HF is considered a weak acid. There are 2 perchloric, again, perchloric and chloric acid. So HClO3, HClO4, again, 3 and 4, a lot of oxygens there. And then nitric and sulfuric, those are the strong acids. What you will notice is those are all around oxygen, except for, so they're all nitrogen, sulfur, chloride, and bromide, and iodide. So like all right near oxygen, right in that corner of the periodic table. So those are considered the strong acids. You need to know those. They're strong acids because they completely dissociate. So know that list. It's not that long. Just kind of take a look at the periodic table and kind of line it up and recognize why it's strong. Okay. All right. And by the way, you know that nitrates, we know that nitrates and sulfates are soluble, and so they're completely soluble. That's why we expect those to dissociate. All right. So to show the dissociation of the following strong acids in water, H+, aqueous, and Cl- aqueous. Easy enough. So do the others. Okay, watch out for H2SO4. These guys are the same thing, K+, aqueous, and OH- aqueous. The reason that we're talking about these is because these are the acids anyway contain H+, they don't contain a metal, but they're still ionic. So acids, bases, and solubles are considered ionic compounds. So write out the solubility for the rest of those. Weak acids, on the other hand, only partially dissociate. And weak bases only partially dissociate. Again, I'm going to do the first one, and then you can do the rest. HNO3 dissociation to H+ and NO2-, both aqueous, but because they only partially dissociate, you can produce this, but these two can come together and reform that. Again, you have like 5% of it in this form and like 95% of it in this form. So again, we'll get into acids and bases more, but you need that double arrow when you have a weak acid. How do you know something is a weak acid? It is not a strong acid. So you know the 7 strong acids, everything else is weak. If there's H out front, it's a weak acid. All organic acids, weak acids. Okay. Okay. Weak bases, same thing. Anything that is not a group 1 or heavy group 2 hydroxide is considered a weak base. NH3 is an important one. It is a base, okay, base, and we're going to talk about that in class. Okay. So now that we understand, so the precipitation, just rewind a little bit. Precipitation reactions involve soluble ionic compounds. Neutralization reactions involve acid and base ionic compounds. So the process is going to be the same. I'm going to have an acid combined together with a base. Okay, and I'm just going to highlight, there's my sodium, there's my chloride, the end result is the sodium and the chloride. Actually, I'll do water first. So again, I have this dissociates into H plus and Cl minus. This dissociates into Na plus and OH minus. And so now, just like before, they're going to switch partners. So hydrogen was with chlorine, but this time hydrogen is going to combine together with the only other thing that it can join together with and give me HOH. HOH are the H plus and the OH minus, but of course that combines together to give me H2O. Oh, by the way, these are both aqueous. These are both aqueous. Water is going to be liquid. Water can't dissolve itself. So a water molecule can never be aqueous because it's got to be a liquid. It can't dissolve itself. Okay, next up. Now I'm going to combine together my chloride ion with my sodium ion, and I'm going to have NaCl, which turns out to be aqueous because it's group 1. So there's my salt. Okay, so water plus salt, that's what your acid and base reaction is. Okay, so that's essentially, so rewrite the reactions here. What do we end up with? And what you always do is if you eliminate, if we just focus on, we just did this example, but if we take a look at H and OH, your salt is always going to be what remains. So H2O liquid plus NaCl aqueous. So we can do the same thing for this one. H and OH are going to combine together to give me water. That means my salt is going to be the ions that remain. Okay, good. So do the rest of those. Formation of gases. So there are a couple that are actually pretty interesting. So if you end up with any of these as products, if you end up with any of those as products, they immediately turn into these. Okay, so if you're doing an acid-base reaction and you find H2CO3 as a product, you are going to form CO2 gas. You could form SO3, you can form ammonia, or you could form H2S. So if you end up with any of those as products, they immediately form gas and leave behind water in the gas. So the gas just disappears and bubbles up. Okay, so just be aware of those, that when you end up with those in a metathesis reaction, you have to kind of take one extra step and switch this thing. You basically, substitute out this right here for that. Okay, so you take one and replace it with the other. So write the complete molecular equations for the following. And again, these are all going to do something a little bit different. So be aware that when you create these things, you should probably go back to this list. Okay, and we're going to work on this in class. Good. Okay. This is long, and I'm going to actually, well, I'm not going to stop it. I'm going to keep going, but you might want to pause it, take a break, because we still have to get through oxidation and reduction reactions. Again, there's a lot here, so I want to make sure that this is part of the exam 1, and then we're going to do the other stuff a little bit later. So oxidation reduction reactions. So these look a little bit different. By the way, metathesis reactions were called double replacement because you replace two, you take two things and they both switch partners. Oxidation reduction reactions, we're going to see electron transfers from one reactant to another. And those are going to be single replacement reactions where we actually have just one partner change. So oxidation is the loss of electrons. So anything that is oxidized is going to lose electrons. So if I have an iron compound and it starts as neutral iron and it turns into iron 2+ aqueous, it doesn't have the rest of it, but that's fine. It has gone from a charge of 0 to a charge of 2+. That means it lost 2 electrons. I'm positive I lost an electron. It became more positive it lost an electron. Reduction is the gain of electrons. So fluorine minus, fluorine going from F to F minus, this has gained 1 electron. Okay, so it's gone from F to F minus, and we're going to learn how to take care of those in just a bit. And so is the gain of electrons. Everyone has kind of their own mnemonic for memorizing this. The one that I was taught at the beginning of my career, oil rig, oxidation is loss, reduction is gain. The other one is Leo Ger. So Leo Ger. Loss of electron is oxidation, gain of electron is reduction. So however you want to do it, it's an easy way to memorize it. And so oxidizing agent and reducing agent. So this is a little bit strange. So let's just take a look at oxidation and reduction. One is losing, one is gaining. So the oxidizing agent, and please bear with me here, oxidizing agent is the substance that is itself reduced. And then the reducing agent is the substance that is itself oxidized. Essentially, think about it this way. The oxidizing agent is responsible for the oxidation. Therefore, it has to give up electrons, or it has to gain electrons from that oxidizing thing. So the thing that's doing the oxidizing is taking the electrons from the thing that is oxidized. Okay, so we're going to see this. Maybe we'll see this better when we kind of look at a couple of these examples. But so let's take a look, a single replacement reaction, and we're going to identify what is oxidized, what's reduced, and kind of draw some arrows here. So first of all, you're always going to start with an element and you're going to end up with a new element. That's the single replacement part. So I have aluminum here and I have hydrogen. Okay, so those are both the cations. So if you have two cations, two potential cations, that means on the other side, they're going to switch partner. So the aluminum and the hydrogen are going to switch. So I'm going to have hydrogen here and I'm going to have aluminum here. I know that aluminum comes as a 3+. Okay, so aluminum I know wants to be aluminum 3+. So that means that how many chlorides? So if I combine that together with chloride, I should end up with AgCl3. Okay, and what we know about chlorides is they are all aqueous. Hydrogen, so I have aluminum as a solid, neutral. HCl is aqueous, it's a strong electrolyte, and we're almost finished. I have hydrogen because I started with this element. Aluminum is an element, and I know it's going to be exchanging with hydrogen. Hydrogen also has to be an element. What form does hydrogen come in as an element? H2, and we know it's gas. So you're going to have to basically say, all right, I've got an element on one side. What's the element on the other? In this case, it's going to be H2. So that was the exchange that we had. What exactly happened? So aluminum was neutral. It has that 0 charge. Okay. Here I have Cl minus, H plus. Over here, hydrogen is neutral, right? Hydrogen does not have a charge. It is going to be a 0 charge. Let me just use a different color for that. 0 plus minus, and it is neutral over here. Okay. So H2 is neutral. Anything in its elemental form has to be neutral because it has to be neutral. And I know that chloride is -1 and aluminum is 3+ when it's in a compound. So aluminum is neutral when it's by itself. It is neutral when it's by itself, and it is charged when it's in a compound. Hydrogen has a charge when it's in a compound, and it's neutral when it's by itself. So aluminum goes from Al0 to Al3+. Did it gain or lose electrons? It lost electrons. It lost how many electrons? 3, in fact. And we're not really going to worry too much about charge just yet. It lost 3 electrons. 3 lost electrons. That means that aluminum lost electrons. So if I know it oxidized, what's reduced? The oxidizing agent and the reducing agent. So what is oxidized? Aluminum, the element, is considered oxidized. Okay. All right. Aluminum, the element, is considered oxidized. Let's take a look at what we got left. Hydrogen, we know, is the one that exchanged. Hydrogen goes from +1 to 0, so it has gained an electron. And if it gains an electron, that means that hydrogen itself is reduced. So now let's take a look at the extra question of what is the oxidizing and reducing agent? So one thing, first of all, one, it can only be reactants. Two, it must be the whole compound, including phase. What do I mean by this? Well, so if it's got to be one of these two. So, and this is the best way to do it. So if aluminum is the oxidizing agent, so if aluminum is oxidized, that means that it is going to be the reducing agent. Therefore, what compound is a product or is a reactant that contains aluminum? Aluminum solid is going to be considered the reducing agent. So aluminum, the element, is oxidized. Aluminum solid is the reducing agent. Okay, so the entire product has to be. Hydrogen itself is the thing that's reduced. It is considered, whatever it is in, is considered the oxidizing agent. HCl aqueous is considered the oxidizing agent. Okay, or another way of saying it, because if we wanted to just ignore the chloride because it doesn't change, we could say the H+ ion is considered, but either one would be correct for the most part. Okay, so again, the oxidizing and reducing agent must be the reactant only and must be the compound including the phase. So do the same thing, exchange these, exchange the metals in these cases, and write the products. So how do we know that these reactions actually occur? So the thing about it is we have this thing called the activity series. And so what we have is we have a series of different metals and their reactivities. So take a look at this and see what we actually see. Lithium, potassium, barium, calcium, sodium, as we're going down, are increasing in reactivity. So ease of oxidation, we have the most reactive at the top, and down at the bottom, gold is the least reactive. By the way, this is related to battery technology and the amount of electrons and energy. We're going to get into that when we get to electrochemistry, but lithium is incredibly reactive, which is good for batteries because it produces a lot of potential energy, and it's really light. So lithium is the most reactive, gold is the least reactive. What you're going to notice is we have lithium, potassium, sodium, and those are all what? They're all group 1, okay? Next you have barium, calcium, magnesium. Those are all group 2. And then we have aluminum, manganese, zinc, chromium, iron, cobalt, nickel, tin, lead. Tin and lead are probably separate, but aluminum, magnesium, zinc, chromium, iron, cobalt, they're all metals not in group 1 or group 2, right? And tin and lead are in the main group, okay? And then we've got hydrogen dividing them up. And then finally, the last little bit, we have the coinage metals. And that's why it's important to differentiate between the coinage metals and everything. So copper, silver, mercury, platinum, and gold, those are the least reactive of the group. So there is some rhyme or reason to this. You generally will get one of these tables in order to determine it, but group 1 and group 2 are pretty high on the reactivity scale. Transition metals, coinage metals, broken up by hydrogen. Why am I giving you guys the reactivity of these things? And I'll just highlight hydrogen as well. Why am I giving you the reactivities? Well, when we're creating these reactions, the ease of oxidation equals the ease of reactivity. Those higher on the list prefer to be ions. Okay, so the more reactive is ions. All right, we'll prefer to be ions. Okay, what this means is if I'm looking here and I have magnesium, and I have hydrogen. Okay, let's find magnesium and hydrogen on the list. Here's my hydrogen, and here's my magnesium. Which one is higher on the list? Magnesium. Magnesium is higher on the list. So what I'm expecting is magnesium to be an ion in the product. So the more reactive should be a product. Yeah, should be a product. I'm sorry, should be an ion in the product. So we see magnesium is a solid, it's a metal, and as a product, the magnesium is aqueous, meaning this reaction will occur. Will occur as written. So as long as the one that's higher in the list, the more reactive is in an aqueous phase or an ion is a product, then the reaction is going to happen. So same next question, copper and zinc, which one is more reactive? Okay. Aluminum, copper, which one is more reactive? As long as the more reactive is a product, you are going to, so you're either going to have a reaction occurs or a reaction does not occur, right? So no reaction. So decide if these two are going to have reactions occur, okay? Decide if these reactions will occur. And of course, you have to figure out what their products are, okay? And then finally, balancing of redox reactions. It's really fun. It's actually really enjoy doing it, but we're going to save that for electrochemistry way back in chapter 17. So we can come back to this. We're going to talk about oxidation and reduction again, but that's what I want to focus on. All right. Yeah, that was a really long video. And this is probably where the second test is going to stop, or at least we're going to have some time before we get into reaction stoichiometry.